good afternoon, everybody, and thank you for tuning in to our Astronomy 102 vodcast. My name is Melody, and I am a science educator. On a regular day before we began working from home, I would be outdoors in our eco garden studying nature or in a lab looking at life through a microscope. So, in today's episode, we will be embarking on a journey to explore the universe. And together with me, first I have my colleague Ferry.
Hi everyone, it's me again. And just like Melody, I'm a science educator and I usually teach the physics and chemistry workshop. You might remember me from the first and the second episode of the podcast. So today I'm back for more.
And we also have a special returning guest, Pisha.
Hi, thank you, Melody and Ferry, and the rest of the Science Center team for once again inviting me to be a guest here at Astronomy 102. And hello to everyone who's watching at home. My name is Percier Decierdo. I am a science communicator at the Mine Museum in Manila, in the Philippines. And at the Mine Museum, I specialize in sharing the wonders of the universe to our museum audience. It is my pleasure to do that here in this podcast.
Thank you for joining us once again, Pisha. We really appreciate it. So for today, Pisha will be sharing his astrophysics knowledge with us as Ferry flies through the universe using a computer simulation. And just like our previous vodcast episodes, if you have any questions related to our topic, which is exploring the universe, you can submit your question using the link in the video description or in the pinned comments. We will try our best to answer your question, but please give us some time.
That's right. So today I will be taking the role of a spaceship captain. Thanks to science, technology, and a little bit of imagination, journey through the universe that would span hundreds, if not thousands of light years can be done in mere seconds.
Ooh, hang on a minute. Did you say light year? So how many days are there in a light year?
Okay. Although there is a year in the word light year, it's actually a measurement of distance. It's not a measurement of time. I believe Pisha can explain this better to the audience.
All right, thank you, Ferry. So yeah, as Ferry said, light year is not a measure of time. It is a measure of distance. So 1 light year is the distance that light travels in 1 year. Now, light is very fast. So in vacuum, like in the emptiness of space, it travels at 1 billion kilometers in an hour. So light traveling in vacuum at that speed can circle the whole Earth in 7.5 times in 1 second. So just imagine 1 second like that. Light has already circled that Earth in 7.5 times. So in fact, light can travel from the sun to the Earth in only 8 minutes and 20 seconds. And it can go from the sun to Pluto in 7 hours or less. So 1 light year is a very long distance. Specifically, 1 light year is 9.5 trillion kilometers approximately. Written in the long way, that's 95 followed by 11 zeros.
Wow. Thank you for the explanation, Pisha. Now that we know how far 1 light year is, I hope we can appreciate more about the immensity of our universe as we embark on a journey through it. Let me load the simulation. Right, now that the simulation is loaded, I cannot think of a better starting point than our home planet, the pale blue dot that we call Earth. Although it's not, how do I say this? Although it's not a very significant planet, we compare it to other planets in the universe, it is actually a very, very significant planet to us because the Earth is the planet that we know of so far that can support life.
So what makes the Earth able to support life?
Well, for starters, the Earth has atmosphere, right? And that atmosphere contains oxygen. Now, you all know that we need oxygen to survive, right? Now, of course, there is also liquid water. And fun fact, Earth is one of the few places in the universe in which water can exist naturally in all three states. So we have solid water, ice, in the North Pole and the South Pole. We have liquid water all over the place in our ocean. In fact, the Earth is 2/3 water, right? And then, of course, we also have water vapor, and that can be found in our atmosphere. And all of this is possible because the Earth is located in the Goldilocks zone.
The Goldilocks zone. Wow, what is the Goldilocks zone? Pisha, maybe you can explain it?
Yes, thank you, Melody. So yeah, the Goldilocks zone is this region around the star where the temperature is just right for liquid water to exist on the planet. So if you can get too close to your star, it is too hot that all of the liquid water evaporates. But if you're too far, liquid water is just frozen as ice. But in the Goldilocks zone, the temperature is just right where water can be a liquid.
So basically, not too hot, not too cold, just right.
That's very interesting. So, is there any other planet in our solar system that also belongs in the Goldilocks zone?
Yes, Melody, as a matter of fact, there is. Mars is actually inside the Goldilocks zone. It's in the outer edges of the Goldilocks zone. And that is one of the reasons why scientists are very interested and very keen on studying Mars. Ultimately, scientists want to know if there's life on Mars right now or if there has been life on Mars in the past. And that's why we send lots of probes to Mars because we want to find evidence of life on the red planet.
Mm.
And of course, liquid water has also been found on Mars back in 2015. So that adds to the long list of reasons why we should go to Mars and check it out.
Wow, that's very exciting. So, if you all still remember our previous podcast about life in space, we did also talk about how liquid water is essential to life as we know it.
Yeah, that's right. In fact, our planet is not the only planet that is conveniently related in its star's habitable zone, which is the more technical term for the Goldilocks zone. So in 2015 and 2017, astronomers discovered a total of 7 planets with properties similar to Earth going around an ultra cool red dwarf star called TRAPPIST 1. So, Ferry, with the simulation, would you be able to fly us to that star?
That would be my pleasure.
So while Ferry is taking us all the way to TRAPPIST 1, I would like to welcome those of you who have just joined our vodcast. If you have any questions related to our topic today, which is exploring the universe, you can send that to us using the link found in the description or in the pinned comment. Are we here yet?
Yes, we are here.
Yeah, we are here. Yeah, so check out that ultra cool red dwarf star called TRAPPIST 1. We call it ultra cool not just because it's very cool, although it's that too, but also because as far as stars go, it's not one of the hottest. Of course, still it's very hot because it's a star, but by stellar standards, it's not very hot. So actually, we have discovered planets going around this star. Scientists have discovered a total of 7. There might be more, who knows? But so far, we've discovered 7. And these planets have temperatures that range from minus 103 to 57 degrees Celsius.
Huh, that's almost as cold as my ex-girlfriend's heart.
That sounds pretty cool. Do you mean the star or or your ex's heart?
It can go both ways, I guess.
Actually, with the right equipment, we could we humans could live on some of these planets.
Yeah, so those are really, really cool, right?
Yeah. Um, yeah, they are really cool. And since it's, negative 103 degrees all the way to 57 degrees Celsius, I think those are some of the coolest planets I've heard of today. Coolest.
Oh my god.
So, how far is this TRAPPIST 1 from our solar system?
Well, TRAPPIST 1 is, by human standards, quite far from us. It is around 40 light years away from the solar system, but it's still located within the Milky Way galaxy. So, Ferry, will you be able to zoom us out to show the whole Milky Way galaxy and to show where our solar system and TRAPPIST 1 are?
Well, yes. So I'm going to zoom out from TRAPPIST 1 all the way so that we can see our galaxy, the Milky Way. Okay, now it might be a little bit dim, so I'm going to make things a little bit brighter after this. And what I'm going to do next is that I'm going to center the view to where the Earth is, okay? And I want you guys to see how much the X mark has moved, okay? All right, making it brighter first. Can you both see the X mark?
Yep.
Okay, so that's where
that's where
TRAPPIST 1 is.
Yeah,
Yep.
okay.
Yeah.
And then let's go and center the Earth.
Okay, but But that didn't even really move at all. It was just a small little blip. Okay, so if we look at it from this scale, it really doesn't seem like they're very far apart at all. But I guess if we do the math, it is really very, very far. So, Pisha, just now you mentioned that the distance is almost 40 light years from our solar system. So, does that mean that if we build a spaceship that is somehow capable of achieving the speed of light, it would still take us about 40 years to get there?
Yeah, that is correct. But that's a big if. If we can build a spaceship that can travel at the speed of light. But actually, it's not possible in physics to build a spaceship that can reach the speed of light.
Oh, and why is that?
Well, according to our best theories of how the universe works, like the theory of relativity by Albert Einstein, nothing that has mass, like a spaceship, can travel at the speed of light. According to these theories, it would take an infinite amount of energy for something with mass to travel at the speed of light. But light can travel at the speed of light because light does not have mass.
Ah, okay. So then, what do we have around our galaxy? So our galaxy is the Milky Way, right? So do we have any other neighboring galaxies?
Well, yes. In fact, the Milky Way is surrounded by a bunch of dwarf galaxies. They're sometimes called satellite galaxies because they go around our galaxy. The biggest of these can be seen with the naked eyes in a dark sky. It's called the Large Magellanic Cloud. But the
Mm-hmm.
closest major galaxy to us is the Andromeda Galaxy. It is located around 2.5 million light years away from us.
Wow. Ferry, can we see that using the simulation?
I'm gonna answer that by quoting Barack Obama. Yes, we can. All right, so I'm bringing you to Andromeda Galaxy. Now, see how similar it is in shape compared to our galaxy? It's
Mm-hmm.
kind of similar, right?
Yeah.
Yeah, so fun fact, we don't actually know what our Milky Way galaxy looks like since, none of our spacecraft have actually been outside of it. Okay, so this shape, okay, the shape that you saw just now of the Milky Way, it was actually estimated based on the shape of other galaxies that we can actually see using our telescope. Isn't that right, Pisha?
Yeah, that's right. So actually, we don't have a picture of our own galaxy, the Milky Way, because it's so hard to travel out of the Milky Way galaxy. And we don't have a selfie stick long enough to take a selfie of our own galaxy. So, yes, so our guess of how our Milky Way galaxy looks comes from studies about like where other stars are located within our galaxy, but it also comes from the way we study other galaxies. So by looking at the shapes of other galaxies in the universe, we have a guess about the shape of our own galaxy. And now, before we go to the next point, one reason why it's hard to determine the shape of our own galaxy is we can see it from the simulation here, shown by Ferry. If you see, there are dark lines in in the Andromeda galaxy that gives it like arms, spiral arms. So
Mm-hmm.
those dark lines are actually gas and dust, and it's hard to see through that gas and dust. And it's the same with our Milky Way galaxy. So since we're inside that galaxy, the Milky Way galaxy, it's hard to see through it, which is why it's not the easiest to determine the exact shape of our own Milky Way galaxy.
Ooh, okay. Wow, there's so much we don't know about the universe. So right now we are so far away from Earth in the simulation, but can we go even further?
Yes, we can. Now I'm going to fly further away from the Milky Way and the Andromeda Galaxy. And as I'm flying away, okay, I want you to know something that at this scale, okay, all of the dots that you see, okay, the big ones, the small ones, the bright ones, and even not the not so bright ones, they no longer represent stars. They actually represent galaxy. And each of these galaxies, okay, they have millions, if not billions of stars in it.
Wow. So, Prisha, how many stars are there in our galaxy, the Milky Way?
Well, within our own galaxy, the Milky Way galaxy, there are around 400 billion stars. That's four followed by 11 zeros.
Wow.
400 billion. So if Jeff Bezos, the CEO of Amazon, could buy each star for $1, that's quite a deal, $1 per star, he would still be short of 250 billion to buy the whole Milky Way galaxy. And that's just one galaxy, the Milky Way. Now, many of these stars in the Milky Way galaxy have planets around them. And some of them are very similar to the sun. So who knows? Some of these planets might have life around them that we are just yet to discover.
I mean, that's pretty mind-blowing, isn't it? Like sometimes I think about it and I get goosebumps, you know. Either we are alone in the universe or we are not. And to me, both possibilities, they are actually equally very terrifying. Don't you agree?
Oh, yeah. Yikes. That is terrifying indeed. So, another question for Pisha. How many galaxies are there in the universe?
Well, actually, the short answer is we don't know. We don't even know how big the whole universe is. But we do have some idea about how many galaxies there are in the observable universe. So within the observable universe, there's around 2 trillion galaxies. That's 2 followed by 12 zeros. 2
Wait,
trillion galaxies.
wait, you mentioned the term observable universe. So, what does that mean? Does that mean if I look through a telescope, I can see all of these galaxies?
Well, the observable universe is the part of the universe that we can detect with our detectors. And some of these detectors are telescopes. In fact, that's the general term that astronomers use for detectors. They're called telescopes. But not all of these telescopes are the kinds of telescopes we imagine when we think telescopes. Some of them are radio telescopes and so on. So it is around 93 billion light years across this observable universe, the whole part of the universe that we can detect. 93 billion light years across.
Wow.
Yeah, we cannot see the part of the universe that is beyond the observable universe because there has not been enough time since the Big Bang for light from them to reach us.
Oh, okay. Can we then see this observable universe in the simulation?
Yes. So right now we are looking at the observable universe. Now, I want you to take a look at this shape here. Does it resemble a pair of butterfly wings to you?
Um, yeah, okay. So if we look in the middle where the black space is, that would kind of be like the body of the butterfly, and then the galaxies on either end form the butterfly wings like this.
That's
Is
right.
that what we're referring to?
Yes.
Yes?
So some of us from
Ooh.
the observatory actually call it the cosmic butterfly. And this is the shape of our observable universe.
Okay. So then what lies beyond this?
Well, that's the thing. We don't know. And as Fisher has said before, literally only time will tell.
Ooh, okay. Wow, that's really amazing. So, to those of you who are watching, I'm sure you find this amazing as well, right? So, if you have any questions, please send them to us using the link in the description or in the pinned comment, and we will answer them very, very shortly. So, Pisha, you have an astrophysics background, right? So, what is the most astounding fact that you can share with us about the universe?
Wow, that is actually, it's hard to pick. There's so many. But I guess one thing that I find really astounding, and we can see it here in the simulation, is the fact that there's so many stars in just the observable universe. Like every dot there, as Ferry mentioned, is a galaxy. And in each of those galaxies, there's so many stars, and many of these stars have planets going around them. And that means there's so many planets in the universe. So to me and to many other scientists, that suggests that it is likely that there's other life somewhere out there in the universe. And I'm very curious what form that life takes, like what molecules are they made of, what is their biochemistry. And I'm even the most curious about whether some of that life is intelligent, right? So are there intelligent beings somewhere out there? In other words, is there an extraterrestrial intelligence somewhere else within our galaxy or maybe in another galaxy or in a galaxy far, far away, right? Like the one shown here. So that's something I've always been pondering about. Like, are we alone in the universe or not? Are there extraterrestrial intelligences? And do they also hold podcasts or podcasts like this to ask these same questions?
Wow, that is really astounding indeed. Ooh, my mind is a bit blown. So, Ferry, you have a chemistry background. So, what is your fact?
Well, mine is a little bit different compared to Pisha. So mine is related to the elements of the periodic table, right? So the two most abundant elements in the whole universe, they are hydrogen and helium. So they are the lightest elements, okay? And other heavier elements like carbon, nitrogen, oxygen, elements that make up living things, okay? They are actually formed when hydrogen and helium combine. They undergo this reaction called the fusion reaction. And in this process, a ton of energy is released. Now, this fusion reaction usually happens in stars, and the energy is what makes stars so hot and so bright. Now, metals like iron, right? Iron can only be formed when a star has used up its hydrogen and helium. And this also means that the star is close to the end of its life cycle. So we have iron in our body, right, Melody?
Yes, we do.
Yeah. That is in our blood. Okay,
Yep.
there's this thing called hemoglobin. Now, we use it to transport oxygen, and basically, without it, we cannot be alive.
Mm-hmm.
Now, that being said, the iron in our blood was forged at the heart of a dying star. And the only way for iron to get to the planets is if the star dies and goes supernova, meaning it explodes and then it scatters all the elements across the solar system. So stars die so that we can live. And to me, that is the most poetic thing about the universe. Don't you agree?
Yeah.
Okay, Melody. So you are probably the odd one out here, right? Since you have life science background. So I believe you have your own astounding fact. Do you want to share that with us?
Yeah. Okay, so actually, Ferry, the connection between astrophysics, chemistry, and biology or life sciences is stronger than what we think it is. So, just like what you mentioned, the elements that make up our bodies come from exploding stars, which sometimes we also call stardust. And the thing is that these explosions, they are still going on even right now as we speak, meaning that stardust actually continues to float down and land on the earth. So our bodies, they actually continuously regenerate themselves. And okay, so that doesn't mean that, let's say, if you cut off a limb, it will grow back just like what we see in the movies. But our cells, they age and they eventually die. So that actually means that they need to be constantly replaced. So for example, our skin cells, they last only a few days, but our red blood cells, the ones that you mentioned containing hemoglobin, they only last up to 3 months. So when our bodies need to replace these cells, they use the nutrients that we get from our food to make the cells. And these nutrients, if we look at the core basis of them, they are made up of elements, which is also stardust. So, and remember, stardust is still finding its way to Earth today. So, some of the material that makes us is as old as the universe, but some of it can actually only have landed here maybe only a few hundred years ago. And that's what I find really astounding because, we're all made of stars. Speaking of which, think about it. When we observe stars in the night sky, aren't we actually observing ourselves?
Well, I guess if you put it that way, then yes, we are the universe observing ourselves, right?
Yeah.
Yeah, see, isn't it cool like how no matter which field of science you're in, you actually have a piece of information about the universe? And then when we get together like this and we collectively share these facts, we actually form a more complete picture of the universe. And we can use that to understand about our place in it more.
Yeah, I agree. Oh, I feel really mind blown. Okay, so now I think it's time for us to answer some questions. So let's look at the questions that we have received. Okay, so our first question here from Sophie is the Milky Way has so many stars, so then why is TRAPPIST 1 special? So perhaps, Ferry, you could answer this question?
Okay, so TRAPPIST 1 is special in the sense that it's an ultra cool star, meaning, I mean, it's still hot, okay, being a star and all, but it's cool. It's cooler compared to other stars. And around it, we have found 7 planets, okay, and all these 7 planets, they are in the right temperature Okay, they belong in this zone called the Goldilocks zone, as Pisher has already explained. So potentially, these 7 planets, they are able to support life as we know it. So in that sense, I guess this star is really special.
Hmm. Okay. Okay, next question that I have for Pisha. Okay, and this is kind of a long question, and it's also from Sophie. So, okay, so if stars are moving towards each other and galaxies they're also moving towards each other, which one will
Mhm.
happen first? Will the sun hit the next nearest star first and start an apocalypse that way, or will the Milky Way collide with Andromeda and start an apocalypse that way?
Yeah, that is an excellent question. So, curiously or interestingly, galaxies in general are actually moving away from each other. So, if you
Ooh.
look in general at most of the galaxies, they're moving away from us. And the interesting thing is, the farther the galaxy, the faster it's moving away from us. And that is what gives us a hint that there was a big bang, that the universe started as a small atom sized or even subatomic sized entity and just expanded into the universe we see today.
Hmm.
But the exception to that rule is the Andromeda galaxy, our neighboring galaxy. And this, the question I think that Sophie has, it's the fact that Sophie has in mind when she asked this question. So the our neighboring galaxy, the Andromeda galaxy, is actually moving towards the Milky Way galaxy. Now the question is, what will happen first? So, will another star collide with our sun? Actually, that
Hmm.
is not very likely, especially for the stars within our Milky Way galaxy. But even for the stars of the Andromeda galaxy. So, when the Andromeda galaxy and the Milky Way galaxy collide millions of years into the future, so that's a very, very long ways off. When they collide, it's just the galaxies colliding. That's the interesting thing. Because the space between the stars is so far apart. Like our nearest star is more than 4 light years away, and most stars are even farther. So because of the distance between stars, when two galaxies collide, they'll just pass right through. Like it's very rare for stars to
Hmm.
actually hit each other. That's the interesting thing. So most of the collision will happen between the gases and clouds within the galaxy. And when they collide, that will actually trigger the formation of newer stars. So I hope that answers the question, I guess. So let me summarize. So when the Milky Way and its neighboring galaxy Andromeda collide, it's super, super unlikely, very low probability for our sun to hit another star.
Okay. So, right. Okay. So, okay. Next, we have a few questions about, I believe, black holes. Okay. So we have a question from Phil that asks, can you explain about the black hole and the possibilities of stars inside a black hole? Okay. But first, I think we got to get what a black hole is out of the way. Okay. So maybe Ferry could explain to us what exactly is a black hole.
Wow, it's a tough one. Okay, so black hole is an object that we have in space. It's a real object. Okay, it's something that is very, very massive and something that is very, very dense, like some of my friends. And because it's so massive and so dense, it has got very, very high gravitational pull. Right now, this gravitational pull is thought to be bending, okay, the fabric of space-time itself. So you can think of it this way. Imagine you are changing your bed sheet, right? Like you stretch your bed sheet, okay, the bed cover. And then as the bed sheet is being stretched, okay, you put a bowling ball on top of the bed sheet in the middle. So you will see that the bed sheet will be warped, right? You can see that the bowling ball is
Yeah.
making indentation. So that is, in that sense, how black holes warp space-time, okay? And because of this, okay, black hole actually, how do I say this? Light cannot actually escape black hole, and that is the reason why it's called black hole, because well, it's black. Light cannot escape from it. Now, in our Milky Way galaxy, okay, scientists thought that there is a supermassive black hole called Sagittarius A at the center.
Mhm.
Let me see if I can show it to you using the simulation.
Oh, that is actually one of the other questions that we have. So the other question that we have regarding to black holes, because I know the answer to this, haha. So is actually what is the bright thing that's right in the middle of the Milky Way? And right now you're actually saying that it is not any bright thing, it is actually a supermassive black hole.
Yes.
Right.
And
So
I
tell us a
think
little
it's,
bit more about this.
yeah, I think it's a little bit too bright. So maybe I'll decrease the brightness a little bit. Wow. Okay. A little bit more so that I can see the black center, and then I'm gonna zoom in a little bit more. Okay, now that black dot at the center of this view here in the simulation, that is
Mhm.
what we call black hole. And the bright rings around it, the one that looks like the ring of Saturn, those are actually what we call the accretion disk. So this is one of the signs, okay, that astronomers look for when they are hunting for black holes. So again, black holes are black because light cannot escape from it, right? So
Mhm.
how do we see something that is black that doesn't allow light to escape it? Well, we look at the things around it. Okay, so that's one, accretion disk. And then another thing that they would want to look for would be gravitational lensing. Okay, this basically means that light will kind of bend around the black hole. I don't know if you can see it from this here, but there is actually a
Oh, right.
bulge,
Yeah,
right?
yeah, we can see it. Yes.
That is gravitational lensing right there.
Ah.
And it's not sci-fi. Okay, let me stress this to you once again. Black hole is not something that is, that's fake or what. In fact, we have taken, okay, or rather scientists have taken picture of black hole before a few years ago. Real picture of black hole. I mean, it was a little bit underwhelming at that time, but that's just how it is. But with better technology, okay, which will be developed by the future scientists or engineers,
Mhm.
okay, we will be able to see clear picture of black holes, actual photographs of black holes in the future.
Ooh, okay. Um, okay, wait, hang on. So then, is it possible that there are stars inside a black hole? So I think that would be pretty unlikely, right?
Well, okay, I think how do I okay there is this thing called the spaghettification. You should have you heard of it before?
Yes, I
Yeah,
have.
okay, so basically anything that gets very very close to a black hole will be pulled apart by its immense gravity.
Mm-hmm.
And I think it was coined by Neil deGrasse Tyson, is that correct, or is it some other scientist? Anyways, um basically what happens is that if an object gets very very close to a black hole, okay, the gravity will pull it apart, okay, atoms by atoms. Okay, imagine if you have object that is maybe this wide, okay, and let's say this part here is closer to the black hole. Let's say the black hole is at this part, okay, so the gravitational field at this side will be so much higher compared to the gravitational field on this side. So in that
Mm-hmm.
sense, all the atoms will be ringed, will be twisted until it becomes a single strand of atoms, like a spaghetti, like a spaghettification. Okay,
Mm-hmm.
and then this spaghetti made of atoms will then be sucked, okay, to the core of the black hole. And for now, we don't actually know what happens at
Ooh.
inside the core of a black hole. I don't know,
So,
Fisher, you have anything to add?
so that's the sci-fi part of it, right?
I wouldn't say it's 100% sci-fi, right, Fisher? I mean, it's backed by mathematics and simulation, but we have yet to see it actually happening. I guess I would put it that way.
Hmm.
Yeah, actually, spaghettification is a well understood phenomenon. And as Ferry suggests, it's when something becomes like a spaghetti, hence the name spaghettification. And it's caused by the fact that when you are close to certain kinds of black holes, the gravitational pull in one part is very different from the gravitational pull in another part. So, for example,
Mm-hmm.
let me just use the closest thing I have here with me, this mug. If this mug is close to the black hole, say the black hole is close to the ground, then the bottom of the mug is closer to the black hole than the top part. And if you're close to a black hole, the difference in gravity here and here is so big. And that very big difference in gravity, the big differences in tidal forces, scientists call it, pulls it into a strand, like a spaghetti, as Ferry mentioned. Now, relating that to the question, would there be stars inside the black hole? And this is where the sci-fi speculation comes in. So everything so far that Ferry said is actually well understood science, but the speculation is, are there stars inside black hole? And the speculation is, um, our universe might be a black hole or might be within a black hole. Because the curious thing about a black hole is that signals cannot come out of it. Light cannot come out of it. Anything inside a black hole cannot escape it, right? There's the surface of a black hole called an event horizon. So inside that event horizon, signal cannot come out. And so it is kind of like a universe, a self-contained entity. So that's the speculation of some scientists, that black holes are mini universes or pocket universes, and that our own universe is inside the black hole. And then again, this is where the speculation comes in. But it's a pretty strong speculation backed by a lot of well thought out arguments.
Mm.
Wait,
Okay.
so if this is true, then the black hole at the center of our galaxy is a black hole within a black hole?
That is curious. Yeah.
Wow.
Might be. It might be. Yes.
I mean,
And of course,
Yeah, that's new to me though. I mean,
yeah.
I've heard of the universe being a simulation run by some higher intelligence being and all that. This is totally a whole new level, man.
Yeah. And I think that could also kind of lead us to our next question from Joshua, which is, what do you think lies outside the observable universe? And would it just be more galaxies or an entire different classification of universe? And I guess if we go by the entire theory of that, our universe is a black hole, maybe outside that is just more black holes?
Huh. So what lies beyond the observable universe?
Or I don't know.
Okay, well, Peter, you wanna take a stab at it first?
Okay, yeah. Well, the simple answer is we don't know, and we can only guess. But the most likely guess is that there's probably more galaxies, just more of the same. Because in science, we have these two very related principles. One is called the Copernican principle in astronomy, and it's that we're not in a special place in the universe, right? The Milky Way is not a special galaxy. The sun is not a special star. Our local neighborhood of galaxies is not special. There's nothing special. So if this is the observable universe, going by that principle, the neighboring air region is probably going to be more of the same. So that's the guess we can make from the Copernican principle. And a related, so by the way, Copernican principle is named after Nicolaus Copernicus, right? So the Copernican principle. And another principle that's related to that is the guess, again, backed by really good thinking in science, is that the universe is homogeneous, the homogeneity of the universe. That means the universe is quite uniform. So yes, it's quite uniform and relatively flat, and things are relatively evenly distributed. It does not look evenly distributed to us at the scale of the solar system, but at the scale of the entire universe, the universe is actually surprisingly like evenly distributed stuff all around. And that's our guess, that beyond the observable universe, it's gonna be quite similar. But again, that's just our guess because we really don't know.
Okay, so let's ask another question a little bit closer to home, maybe. So let's come back to the planets. So how are the planets in our Milky Way named? So maybe let's start from our own solar system. So all our planets, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and Pluto, if you consider Pluto a planet. So how do all of these names come about? Maybe Ferry, you want to answer that?
Well, all of these names, except for one, okay, they are actually named after Roman gods. Okay, like Jupiter, for example, that is the name of the king of the gods. Okay,
Mm-hmm.
and okay, except for one, okay, Uranus. Uranus
Okay
is
lang?
actually the name of a Greek god. So yeah, that's how the name come about.
Okay. Um, cool. Okay. Yeah, I also just learned that today. Okay, so let's look at another question. Uh, okay, so a little bit about stars now, and also a little bit more about black holes. So, firstly, is the North Star the brightest star? So, I think when we look in the night sky, sometimes we can see the North Star. So, is the North Star the brightest star? And maybe Ferry, let's take this question, then I'll pose the next one to Pisha.
Okay, so okay, the short answer is it's not. Okay, in Singapore night sky, uh, the brightest star that we can see that's visible to us, that will actually be Sirius. Okay,
Mhm.
I'm not sure if there is any place in, I mean, on Earth that Sirius is not visible. Then, if that is the case, then probably Sirius is not the brightest star. But still, uh, the North Star, Polaris, is not the brightest star.
Oh, okay. Uh, okay, so next question. Pisha, can you please explain to us, and this question is from Elise. Pisha, can you please explain to us how a star dies?
All right, so how a star dies depends on many factors. It depends on how, especially the most important factor is how heavy the star is. So for stars like our sun, when it is about to run out of its natural fuel, hydrogen, it's gonna go move on to the next fuel, helium, and then to the next after that. So it's gonna keep on using heavier and heavier elements and keep on creating, in fact, heavier and heavier elements, like what Ferry said earlier. And when it does that, our sun will balloon from the star that it is today to a red giant, and then after that it'll just pulse a bit, red giant, and then in the dying stages it will shed off its outer layers, like as shown here. So this is what we call a planetary nebula. The name is quite misleading. It's a misnomer. It's called planetary nebula because it looked like a planet back in the day in telescopes, right? So they
Mm.
called it planetary nebula, but it is has nothing to do with planets. It's the remnant of a star like our sun that has died. So it's going to shed off its outer atmosphere, and that's the colorful um, gas there that we see. And what remains in the middle is going to be what we call a white dwarf star. Like so, in the middle there's a white dwarf star, dim, not very bright star. So that's going to be the fate of our sun. For
Mm.
heavier
Wait, did you say
stars,
dim and not very bright?
yeah.
That reminds me of one of my colleague, but okay.
Okay, yeah.
Dense,
Okay, we're
dim,
not
you
gonna
know.
name any names.
All right, so yeah, that's gonna be what's gonna happen with our sun. It's gonna end up as a white dwarf with a beautiful planetary nebula around it. But heavier stars, what they're gonna do is when they eventually run out of fuel, they're gonna explode. And when they explode, it's what we call a supernova. And in the supernova, it's usually where the heavier elements are forged. So with stars, they forge up to iron, right? But for the elements heavier than iron, they're usually forged in supernovae, right? So if you are wearing a gold ring there, the gold in or like silver jewelry, the silver and gold was forged within a dying star, like literally forged in a dying star, not a living star, but a dying supermassive star. So it explodes as a supernova, and there are two things that could happen after the supernova. What could remain could be a neutron star, which is very dense and not very bright. Yeah.
Okay.
And then after the if it's even heavier than a supernova, sorry, if it's even heavier, then what would end up is not just a neutron star, but a black hole.
Mm. Okay, so since we're back to the topic of black holes, I think Don has a question, and his question is: will shooting stars fly into a black hole? So maybe Ferry, we could just quickly answer this.
Well, I guess if somehow asteroid flies close enough to a black hole, then yes, it will fly into the black hole, and it will basically get swallowed by the black hole.
Mm-hmm. But aren't shooting stars also like things that are burning up in our atmosphere,
Okay,
right?
so shooting star is not actually a star. A shooting star is space rock asteroids.
Yeah.
Okay, that when, for example, it enters our atmosphere, right? It enters
Yeah.
at such a high speed that it basically catch on fire. Okay, because of how thick our atmosphere is. That
Mm-hmm.
gives it the burning effect. Okay, but it's not a star. It's space rock.
Okay. So a shooting star is actually also a misnomer. It's not a star. It's an
Mhm.
asteroid.
Yes.
Okay, cool. So, okay, I think there's one question from Hillary, and the question is, what is a TRAPPIST? So I think in this case, she's referring to TRAPPIST-1, and earlier on we've mentioned that TRAPPIST-1 is a star system that we have actually found to contain Earth-like planets. So that's also very similar to our solar system, right? Am I right? Yes.
Yep.
Okay, so next question then for Pisha. So Don also has another question, and his question is there such a thing as a white hole? So Pisha?
All right, so a white hole is a theoretical idea. So the idea is that it's the opposite of a black hole, right? So if a black hole is a region in space and time where gravity is warped so that nothing can, as long as it's close enough, nothing can escape, not even light. The idea is a white hole is the opposite. So it releases energy. So energy comes from it. And of course, energy cannot be created nor destroyed. So the idea in theory is that white holes are connected somehow via a wormhole to black holes. So that is the idea. And right now, many theoretical physicists and astrophysicists are thinking about it, thinking about what it would look like if it existed, so that they could begin trying to detect it to see whether it really exists or not.
Okay.
Mm,
But as far as we know, it doesn't exist yet.
yeah,
None has been discovered, right?
yeah.
Yes, none has been discovered. Unlike
Yes.
black holes, which we have a lot of evidence for. Like I think a couple of weeks ago, we've discovered a black hole that's not very far from the sun. So when that news came out, a lot of people said, "Oh, now we know what's gonna happen for the rest of 2020." But but actually, that black hole is still a little bit far from our sun. It's just the closest that we've found so far. So that black hole is 1,000 light years away from the sun, if I remember correctly. So it's still far. So it's not gonna engulf our solar system, at least not that we know of yet.
Yeah.
It's
But
quite
looking at
far
how
yet.
things are,
There might be
I
one
hope it
that's
doesn't happen. I
nearer,
hope it
but yeah.
doesn't happen.
Yeah, and it's not likely, fortunately, because again, even though we do not see black holes via visible light, we see their effect on other things, like Ferry mentioned earlier. So yeah, nothing to worry about that relatively nearby, but still actually far black hole.
Mhm.
Mm. Okay, so I think that is all the time. Unfortunately, I think that's all the time that we have for today's episode. So for everybody whose questions we did not manage to answer, you can tune in to our next episode, and our next episode will actually be talking about stars and their life cycles, and we will actually attempt to answer your questions then. So, once again, thank you, Pisha, for spending time with us in today's podcast. And thank you to everybody for tuning in. We hope that you have enjoyed today's episode. So although we are almost at the very end of our circuit breaker period, we are still unsure of whether the observatory will reopen. We will instead try our best to still bring the stargazing experience to you using our live stream, and we hope to see all of you again in our future episodes. So as always, stay home, stay safe, and keep looking up. Bye bye!
Bye.
Bye.